matter as a tracer of geometry. The most persistent intuition about gravity is that matter creates it. A mass appears, curvature forms, and other masses respond. While this description is not wrong, it is incomplete in a way that subtly misleads. It places causality too late in the sequence and gives matter credit for structure. It does not originate. A cleaner narrative emerges when the order is reversed. Space-time geometry already possesses curvature gradients, and matter traces them. Accumulation is not the cause of gravity, it is the visible response to pre-existing geometric constraint. In general relativity, objects in free fall do not experience gravity as a force acting upon them. They follow geodesics, the straightest possible paths permitted by the geometry they inhabit. These paths are not negotiated or chosen. They are dictated by curvature. Once a space-time metric exists, the allowed trajectories are fixed. Matter entering that region does not sculpt those paths from scratch. It discovers them. Motion becomes a form of revelation. Matter shows us what the geometry already allows. This is why treating matter as a tracer rather than an architect clarifies so much confusion. A tracer does not create the structure it reveals. Smoke reveals airflow. Dye reveals currents in water. Dust reveals vibration modes. In the same way, matter reveals space-time curvature by following it. When particles converge, spiral, orbit, or settle, they are not announcing that they have generated gravity. They are marking the contours of the terrain they occupy. Their motion sketches the geometry into visibility. Geodesic motion makes this explicit. Once curvature exists, nearby trajectories either converge or diverge depending on the shape of space-time. This convergence is not caused by particles pulling on each other. It is caused by the geometry between them. Even in the absence of interaction, free-falling particles accelerate relative to one another because the space they traverse is curved. This behavior is central to general relativity as formulated by Albert Einstein and does not rely on any assumptions about cosmology, hidden matter, or early universe conditions. It is a local geometric fact. Accumulation follows naturally from this. Where curvature forms basins, trajectories funnel inward. Matter collects not because it demands to, but because alternatives are geometrically disfavored. Basin-seeking behavior is not an emergent property of matter itself. It is a response to constraint. Over time, repeated passage through the same geometric channels increases density in stable regions, reinforcing the visibility of those basins without creating them in the first place. Matter piles up where it can remain, not where it decides to dominate. This is why the statement mass creates gravity, while useful, is incomplete as an explanation. It describes a coupling relationship without describing the ordering. Yes, mass contributes to curvature, but curvature is already a meaningful object before that contribution is made. Geometry does not wait for matter to become real. The more precise statement is that matter both responds to and modifies existing geometry. Treating matter as the sole origin erases the role of constraint and makes gravity seem like an interaction rather than a condition. By separating this idea from cosmology and large-scale structured debates, the core insight becomes easier to grasp. No galaxy rotation curves are required. No dark matter hypotheses are needed. No assumptions about the early universe enter the discussion. This is a bridge between intuition and mathematics, not a detour into speculation. The mathematics already says that motion follows geometry. The intuition simply needs to catch up. Once this framing is accepted, matter's role becomes clearer and more modest. Matter is not the author of space-time structure. It is the ink that traces it. Where matter flows, geometry guides. Where matter accumulates, geometry permits. And where matter appears to dominate, it is often only revealing a deeper constraint that was present all along. Modern physics already treats matter as a follower of geometry rather than its sole originator, even if this implication is often underemphasized in popular explanations. In general relativity, the fundamental equation of motion for freely falling matter is the geodesic equation. This equation does not describe forces acting on particles. It describes how trajectories unfold once a space-time metric is given. The metric encodes curvature. Matter then moves according to that curvature. The causal arrow here is unambiguous in the mathematics. Geometry defines allowable paths first, and matter traces them afterward. This framework, introduced by Albert Einstein, does not require matter to initiate motion in order for motion to be constrained. Geodesic deviation strengthens this interpretation. Two particles released side by side in freefall will accelerate toward or away from one another depending on the curvature of spacetime between them, even if they exert no force on each other and never interact directly. Their relative motion is determined entirely by geometry. This phenomenon is not theoretical speculation. It is a standard result used to describe tidal effects and gravitational stretching. The particles act as probes. Their separation changes because spacetime is curved, not because they exchange anything. In this sense, matter behaves exactly like a tracer, revealing the underlying structure of the region it occupies. The same logic applies to accumulation. In curved spacetime, certain regions act as basins where geodesics converge. Matter entering these regions will tend to remain there over time because alternative trajectories are geometrically disfavored. This basin-seeking behavior does not require attraction in the traditional sense. It arises naturally from the shape of spacetime. Once again, matter does not need to create the basin in order to fall into it. Repeated passage through the same convergent paths increases density, making the basin visible, but visibility should not be confused with origin. This distinction is already implicit in how gravity is modeled mathematically. The stress-energy tensor contributes to curvature, but curvature itself is defined independently as a geometric field. Matter modifies geometry, but it does not summon geometry into existence from nothing. Treating mass creates gravity as a complete explanation collapses two steps into one and hides the role of pre-existing constraint. A more accurate reading is that matter both responds to curvature and participates in its evolution, but response precedes modification. Experimental confirmation of this ordering appears in the behavior of light as well. Light follows null geodesics, determined by spacetime geometry, bending even in regions where matter density is extremely low. Photons do not create the curvature they follow. They reveal it. Their paths act as clean tracers because they carry no rest mass and engage minimally with matter. Observations of light propagation therefore reinforce the idea that motion responds to geometry rather than generating it on demand. What makes this perspective especially robust is that it introduces no new mechanisms. It relies entirely on the existing formalism of general relativity and on phenomena already measured and taught. No reference to galaxy rotation curves is needed. No appeal to unseen matter is required. No assumptions about early universe conditions enter the argument. The behavior of matter as a tracer emerges directly from the equations of motion and from how curvature is defined. By reframing matter as a revealing agent rather than primary cause, the causal narrative becomes cleaner and more faithful to the mathematics. Geometry constrains first. Motion follows. Accumulation marks where persistence is allowed. Matter does not announce gravity into existence. It sketches the contours of a structure that was already there. This interpretation does not replace established physics. It clarifies what that physics has been saying all along.